previous video, we gave a general idea of how to prove Gauss lemma. Recall that Gauss lemma says that the radial vector field is orthogonal to the geodesic spheres. This is all assuming that we're inside some geodesic ball center at P, right? And we're using some normal coordinates. Inside that geodesic ball center at P, we pick some point Q, right? And then we draw the geodesic sphere through Q center at P. So if we let x be the tangent vector at Q to that sphere, we need to show that this vector, the radial vector at Q, is orthogonal to x under the Riemannian metric. We then proceed to say that our idea is as follows. Our idea is to define a variation, this gamma st of this curve, little gamma v, the radial geodesic connecting P and Q. Then these two vectors here that we're interested in belong to the two main vector fields along this variation. Right? One is the vector field, the velocity vector field along the main curves, and one is the velocity vector field along the transverse curve. These two vectors are just this vector field evaluated at the point Q at 0, 1. The idea of the proof then is to show that this inner product doesn't change when we move these two vectors within that vector field, right, to the point 0, 0. But right at the point 0, 0, this vector will correspond to this vector v, and the other vector is 0. So the inner product at 0, 0 is just 0. And so because this inner product doesn't change as we move these two vectors along here, the original, this inner product, must be 0. So what is missing in there was we never really formally defined this variation, gamma st, and we haven't shown that this inner product doesn't change as we move these two vectors within this vector field, right, along this curve, gamma v. So let's do that. So let us first define this variation, this family, gamma st. Okay, so let V be the preimage of Q under this exponential map, right? What we mean is this unit speed radial geodesic from P to Q has initial velocity V, right? And then remember, by definition of the exponential map, that means Q is the point on this geodesic at time 1. So then we have an isomorphism here between this tangent space to this tangent space at V, right, and the tangent space to M at Q. Now, x lie in this tangent space, and I can let W be the preimage of x under this isomorphism. Alright, so next what I'll do is I'll take a curve sigma on this boundary sphere here in the tangent space, so sigma, such that sigma starts at V and has initial velocity W. Now for HS, right, when we exponentiate sigma s, we get these points here. And if we scale the sigma s by t, right, then we get these radial geodesics. So this gives us a variation of this curve, little gamma. And as we've mentioned before, along any variation, we have two vector fields. One is the velocity vector field along the main curves. We are gonna denote that by t, right? And then we have the velocity vector field along the transverse curve. We're gonna denote that by s. Observe that x is just s0, 1, and this radial vector at q is just t0, 1. Because this t0, little t here, that's just for the velocity vector field, right, along this curve, little gamma v, right, and at point t equals to 1, that's just corresponds to the velocity vector at the point q, so it's this radial vector. And recall that we said that our key idea in proving that this dot product is 0 is by showing that this dot product is independent of t. Right, so we want to show that this is independent of t so that we can evaluate this when t is equal to 0. And when t is equal to 0, s0, 0, right, this change in this direction, s is just 0. Right, so this will be 0. So we want to show that this is independent of t. In other words, we want to show that this partial with respect to t of this inner product is 0. Recall again that we are using the Riemannian connection, which we require to be compatible with the Riemannian metric. So by the compatibility, we have a product rule. So we know that the left-hand side is just going to be equal to. Compatibility was not the only condition we require on the Riemannian connection. For it to be unique, remember we asked that it's symmetric, right? And from that symmetry, we can actually deduce the symmetry lemma, which tells us that this derivative, this covariant derivative, is the same as this. On the other hand, what is this? Now recall that by definition for each s, this t will give us a velocity vector field along the curve gamma s, right? So this dt is just the covariant derivative of that velocity vector field. So that's just the acceleration of the gamma s. But as we mentioned, these gamma s were, because these are image under this exponential map, these gamma s are just gonna be geodesics. So by definition of geodesics, this acceleration must be zero. They shouldn't have any acceleration. And thus, combining these two things, we know that this left-hand side must be equal to this. Again, by product rule, we know that this must be equal to just 1/2 of this derivative. And that this partial must be zero. What does that mean? That means in particular that when we fix any time t0, the speed, these different curves at the same time t0 are gonna be the same. So here in the picture, I'm gonna draw the speed at the time t0 equals to 1. Right, and so in the case when t0 equal to 1, to say that this derivative is 0 is the same as saying that the magnitudes of this velocity vector, the speed at time t0 equal to 1, is the same. So let's see why. Okay, now because these are geodesics, so they must have parallel velocity vector field. On each of these curves for each s, the velocity at any point, right, at any time, must have the same magnitude as the initial velocity. For all of this, we know that this magnitude is equal to the magnitude of the initial velocity. But remember, how did we define these geodesics? Well, we chose them to be imaged under the exponential map. These vectors, right? These vectors. And these vectors all have the same length. It means that all of these geodesics have the same initial velocity. And that means in particular the velocity along each of these geodesics at any point are gonna be the same. This t has constant magnitude. This derivative here is 0, and from that we see that this inner product is independent of the time little t here. So in particular, of this vector here with this tangent vector here x be equal to the inner product of t 0, 0 as 0, 0. Right, so that means that it's going to be equal to the inner product of this vector v with the vector 0, because as 0, 0 is 0. There's no change in the s direction here. So this is 0. And thus we have proven that the radial vector field is orthogonal to the geodesic sphere, which is the content of Gauss' lemma. That we want to use Gauss' lemma in the proof of the fact that geodesics are locally length minimizing, but we will not use the full statement of Gauss' lemma. We will use a corollary. So in the next video, we're going to discuss that corollary.